Good morning, good afternoon, good evening, everyone. Welcome to another installment of the RTDS Technologies User Spotlight series. This is week number 4, and we are excited to bring you 2 presentations from RTDS simulator users today. My name is Katie Sidwell, and I am a simulation specialist on the sales and marketing team at RTDS Technologies. I will just touch on a few housekeeping notes before we begin. If you've already heard these, feel free to grab a cup of coffee or a glass of wine, depending on where you are in the world. So today we will have 2 user presentations that will be about 20 minutes each. And then following that, we will do a live Q&A and discussion. But during the presentations, we welcome you to submit your questions via the Q&A widget. You should be seeing it on your screen. If not, head to the icons toolbar at the bottom and click on the Q&A icon. And if you submit your question this way, we can ensure that it is responded to. And if you're watching this presentation on demand after the fact, please feel free to still use the Q&A widget, and your questions will be emailed to us and we will get back to you that way. So we look forward to receiving and discussing your questions today. We also look forward to hearing from everyone in the chat window. Please feel free to introduce yourself and where you're from. Lots of familiar names and some new ones too. We wish we could see you all in person at our users group meeting or other conferences, but we will take this as a safe alternative option. We have improved our video quality a little bit, so the quality should be a little bit better. But if you have any issues with seeing the details, please feel free to click on the Handouts widget. It looks like a piece of paper in your icons bar, and that brings up the opportunity to download the slides. And that way you can access the slides after the fact and have a look at the details. All right, we have 2 great presentations today from university users across the Atlantic from us. So let's get started. Our first presenter will be Simon Resch. Simon received the BSc degree and the MSc degree in Power Engineering from Friedrich-Alexander University, Erlangen-Nürnberg, FAU, Germany, in 2013 and 2015 respectively. He's currently working as a research assistant at the Institute of Electrical Energy Systems of FAU, where he is responsible for the Microgrid and Energy Storage Laboratory. His research interests include power electronics converters for distributed generation and distributed energy storage systems, battery storage systems, and management of microgrids. The Institute of Electrical Energy Systems of FAU is engaged in the analysis, development, and operation of modern electrical energy supply for research and teaching. The aim of the Institute is a scientific contribution for the design of future sustainable power grids. Please welcome Simon, who will be presenting real-time simulation for PHIL applications in a microgrid testbed.
Thank you for this kind introduction, and hello to everybody online. Today I want to introduce you to the Microgrid and Energy Storage Laboratory of the University of Erlangen-Nürnberg, Germany. And I want to show you why real-time simulation is a key for a flexible and comprehensive testing facility. But first, let's take a short glimpse into our future. This illustrates how a future distribution grid might look like, with decentralized renewable energy infeed and storage systems of different kind and size, just like a typical microgrid environment. Due to the increasing complexity of such energy systems in the future and already today, extended testing methods are necessary to test an electrical equipment not only as an isolated system, but to investigate the interaction with smart distribution grid or a microgrid. Our institute has therefore established a microgrid testing laboratory. The testbed consists of a PV system, 3 energy storage systems, including a lithium-ion, a lead-acid, and a vanadium redox flow battery. The structure is flexible, so that future storage systems can be included, and one remarkable thing is the power hardware in the loop real-time system, which I will come back to in a moment. As I already mentioned, the laboratory includes 3 different storage systems. A PV system of 17 for 2 kilowatt peak on the rooftop of the building, a fireproof container for the batteries, and the necessary measurement and IT equipment. The microgrid is controlled by a central microgrid controller that is based on a Siemens Chem A8000. At the beginning of this year, we integrated a RTDS NovaCore real-time simulator into the laboratory. All in all, a comparably small system that contains just one chassis with 4 cores licensed. The major part of the Institute's RTDS system is used in other projects, but for microgrid applications, this is enough because you have only a few network nodes normally. The most important part, however, is the Aurora communication interface, which enables power hardware-in-the-loop simulation. The RTDS is interfaced by optical fiber Aurora protocol with a 4-quadrant non-linear amplifier from 3-phase, which is now National Instruments. This power amplifier has a rated power of 45 kilovolt ampere and is implemented as a back-to-back structure for energy recovery into the grid. The system is 3-phase with an additional controlled 4th leg to form a neutral line, which is important for hardware-in-the-loop testing with unsymmetrical systems and single-phase connected equipment. The 4-quadrant amplifier can be either controlled as a current or a voltage source. A possible application is the integration of virtual components into the real microgrid. For example, the real microgrid can be augmented by virtual hardware. As an example, further battery storage systems or renewable energy systems. These should be implemented as average models to reduce the complexity of the model. The virtual components, which are simulated in real time, are interfaced with the real grid by the 4-quadrant amplifier. In this case, the 4-quadrant amplifier is operated as a current source, because it does not form a grid itself, but is connected to an utility grid or to a microgrid. The power hardware in the loop takes place over a closed-loop Aurora communication. Another application would be microgrid hardware testing. In this case, the grid is modeled and simulated in real time, and real equipment like power converters, storage systems, or renewable energy systems can be analyzed. Even tests with hardware controllers, for example, microgrid controllers, are possible. An advantage is that the structure of the simulated grid is very flexible, and parameters like voltage, amplitude, and frequency can be simulated, which is normally not possible with real electrical grids. Interfacing again is implemented by the 4-quadrant amplifier, which is operated as a voltage source, in this case, to form the grid. And this type of application I want to show you in more detail in the next few minutes on the example of a hardware PV system that feeds into a real-time simulated grid. The basic idea is to connect the 17 kilowatt rooftop PV system, which is part of the microgrid hardware, to a simulated grid via power hardware in the loop simulation. The advantage of this setup are much deeper testing possibilities for the hardware with less expense than we would have with a real grid. I can perform testing of the grid standards, for example, the German low voltage standard VDE AR 4105 VDE AR 4105, which regulates how a PV converter has to behave in terms of over or under frequency, voltage sag or swirl, blackout, fall right through, etc. Therefore, I disconnect all storage systems from the microgrid bus and I isolate the microgrid from the public grid as well, because the grid will be formed by the real-time simulation now. At the moment of isolation from the public grid, the PV system will recognize that by island detection and shut down to fulfill the standard, not to unwillingly maintain a islanded grid. Here you can see the RS-CAD model for the real-time simulation of the grid. The grid is formed by a 0.4 kilovolt controlled AC voltage source with adjustable voltage amplitude, frequency, and phase angle. And this grid supplies an adjustable RL load. Furthermore, there is a fault logic implemented to apply a fault to the grid. And here you can see the power hardware in the loop branch, which is implemented by a voltage measurement. These voltages are sent directly to the 4-quadrant amplifier to apply to the real microgrid. And here a 3-phase controlled current source is attached, which set points are the currents that are measured by the 4-quadrant amplifier. I will come back to that basic principle just a few slides later. This model is derived from the microgrid tutorial test case from RTDS, and the associated runtime looks like that. We have sliders to adjust the grid voltage amplitude and frequency, to adjust the load active and reactive power, and switches to switch on and off the breakers for the power hardware in the loop branch and the public grid. And we have this push button to apply a 3-phase grid fault with variable fault duration. The most crucial part in power hardware in the loop simulation is the interfacing algorithm. There are many different interfacing algorithms known. The most simple and most straightforward interfacing algorithm is the ideal transformer method, which I applied in this work. It turned out to be stable, but sometimes if instability occurs, additional stabilization can be applied, or another interfacing algorithm has to be applied. Instability can occur from closed loop communication delays. Although we have Aurora communication, there are always some communication delays or other delays from 4-quadrant, from amplifier control or other delays, and measurement noise in the real system or non-linearities in the amplifier. I used a non-linear amplifier. It is also possible to use linear amplifiers, which have better characteristics but have lower efficiency and normally are not built for high powers. And there are many other disturbances that can lead to instability. Well, to explain you briefly the interfacing algorithm, the ideal transformer method, let us assume the left part as to be the connection to the model and the right part to be the connection to the hardware. As I already mentioned, in the virtual part, at the bus where the power hardware in the loop, the PV system will be connected. The voltage is measured, which I will call V virtual, because it is a simulated grid voltage, and this voltage is sent to the 4-quadrant amplifier, which is used as a set point for the voltage which the 4-quadrant amplifier applies to the real hardware. Equally, the current which flows into or from the 4-quadrant amplifier is measured, is filtered and sent back to the virtual part, to the real-time model, where it is used as a set point for the controlled current source, which I showed before, which is also attached to this branch, to this bus, where the power hardware in the loop is connected. And due to this closed loop communication, the real hardware and the model are influencing each other and will therefore lead to an almost real behavior. As I already mentioned, a low-pass filter has to be integrated into the feedback signal to filter the noise from the current measurement. Without a low-pass filter, instability could occur, and therefore I designed a filter with Matlab FDA tool. I used Matlab because it is more convenient to design a filter than in RSCAD. I used a IIR filter to achieve minimum filter order with a passband edge frequency of 50 Hz and a stopband edge frequency of 600 Hz. Here you can see the magnitude response. You can see that in the passband the attenuation is 0 and then drops to minus 80 dB in the stopband. Here you can see the unfiltered signal with all the noise and harmonics, and after the filtering it is a nice sinusoidal signal. The filter is designed with Matlab and then imported to RSCAD via the C builder, which is very convenient. Afterwards I get a black box with the filter characteristics that I can integrate into my RSCAD model. Furthermore, the voltage has to be limited and adjusted. First, a conversion from kilovolt to volt is necessary by dividing the signal through 1000, because RSCAD is calculating with kilovolt and the three-phase system want to have a volt as input and as an input signal. And furthermore, I limited the voltage set point of the 4-quadrant amplifier by minus 700 to 700 volt by an introduction of saturation blocks to reduce the stress of the hardware in case there is some malfunction or some overshoot, so that the hardware there aren't voltages over 700 volt on the hardware. The application is a validation of the PV converter to fulfill grid standards, which I did in the measurement you can see on this slide by adjusting the grid frequency. At overfrequency, the converter shall reduce power, and finally at 51.5 Hz shall shut down. The blue graph is the PV system active power, and the orange line is the grid frequency. Due to the fact that the grid is formed by a simulation, I can freely adjust the frequency, which I did in this measurement. I started at 50 Hz, which is the nominal grid frequency, and at nominal voltage. The converter has to delay the power infeed at a minimum of 60 seconds after a permissible grid frequency and voltage band has been detected. Furthermore, the converter is not allowed to provide full power after synchronization, but has to go this delta. At 1448, the ramp is started, and here you can see a drop in solar irradiance and afterwards the power of the converter goes up to 11.2 kilowatt. Then I adjusted the grid frequency to 51.2 Hertz, which shall reduce power to 40% according to the standard. And indeed, we can see that the converter reduces its power to 6.2 kilowatt. Afterwards, I increased the grid frequency to 51.5 Hertz, which is the frequency which I already mentioned. At this frequency, the converter shall be disconnected according to the standard. And indeed, the power drops down to 0 watt. As a conclusion, I have presented the concept of a test laboratory for microgrid application, storage systems, and further distribution grids. I have shown that it is possible to add virtual components and power grids to the hardware setup to gain a flexible and comprehensive testing facility by real-time simulation. I have shown an exemplary power hardware-in-the-loop simulation of a real PV system that feeds into a real-time simulation of an electrical power grid to perform hardware testing of grid standards, as an example. But there are many more testing applications possible due to the flexibility that power hardware-in-the-loop simulation in combination with a real-time simulation provides. Thank you.
Thank you, Simon, for that great presentation. FAU was actually supposed to be the host of our European Users Group meeting this year, so while it's a shame that couldn't happen, it makes us extra happy to have them as presenters during our User Spotlight series. Thank you, everyone, for submitting your questions so far. As usual, PHIL is a topic of interest for our users, so we look forward to discussing those at the end of the presentation. Up next, we have Dr. Ibrahim Abdulhadi and Dr. Qiteng Hong. Dr. Ibrahim Abdulhadi is a lead R&D engineer at the University of Strathclyde's Power Networks Demonstration Center, PNDC. He received his MEng and PhD degrees in electronic and electrical engineering from the University of Strathclyde in 2007 and 2013, respectively. Ibrahim currently leads a team of engineers and a portfolio of research and demonstration projects in collaboration with UK and international distribution network operators and smart grid solutions suppliers. His work focuses on digital substation architectures, protection and automation, and validation of energy systems, particularly through real-time simulation. Dr. Qiteng Hong is presently a Chancellor's Fellow lecturer in the Department of Electronic and Electrical Engineering at the University of Strathclyde in the UK. His research focus is on novel solutions for protection and control of future power systems with high penetrations of renewable energy sources. Dr. Hong received his B.Eng honors degree in electronic and electrical engineering from Strathclyde and was the top graduate of the year in 2011. He received his PhD funded by National Grid on power system protection, also from Strathclyde, in 2015. During Dr. Hong's career, he has successfully completed or been involved with more than 15 research projects, secured over £1.5 million as principal investigator and co-investigator, with more than 40 publications in international journals, conferences, and technical reports. Dr. Hong was awarded the highly prestigious IET Prize in 2011 for his outstanding academic performance, and he was a recipient of the John Moyes Lessell Scholarship by the Royal Society of Edinburgh in 2013, which supported him as visiting scholar to Hong Kong Polytechnic University. He also held a one-year senior visiting scholarship in Tsinghua University in 2018. Dr. Hong is a regular member in the CGRE Working Group B5.50 and a member of IEEE Working Group P2004. He's the technical lead for the CGRE UK Next Generation Network and occupied the position of Honorary Secretary for the IET Scotland Southwest Committee until 2018. He was also the main founder and led the Global Young Member Showcase in CGRE Paris sessions in 2016 and 2018. Please welcome Dr. Ibrahim Abdulhadi and Dr. Qiteng Hong in presenting design and validation of a wide area monitoring and control system for fast frequency response in future low inertia systems.
Thanks very much for the introduction. Hello everyone. It is a great pleasure to present our work in this RTDS Spotlight series talk. As mentioned, my name is Qiteng Hong. I'm joined by my colleague Ibrahim Abdulhadi. We're going to present a wide area monitoring and control system for fast frequency response. And we're also going to present how we established a megawatt scale power hardware in the loop testbed for validating the performance of the system. Just a quick overview of the presentation. Firstly, I'm going to discuss the motivation and the need for faster frequency response in future low inertia systems. And then I'm going to present the Efcc scheme, which is a wide area monitoring and control system we developed for enabling such fast and coordinated frequency response using different energy resources. I will also discuss how we use a megawatt scale motor generator set to enable a power hardware in a loop test configuration, and how we use such a testbed to validate the performance of the Efcc scheme. In the end, we are also going to share some of the key findings and conclusions from this project. As we know that power systems worldwide are undergoing significant changes in the generation landscape. We have significant increase of wind and PV generation. And at the same time, we are seeing a huge amount of thermal plants being decommissioned in the system. And we also see a lot of new distributed energy resources being connected to the network. So we are facing a totally different system landscape compared to the system we are familiar with before. This map shows the current coal and nuclear power stations in the GB transmission system. As you can see that we still have quite a few of this type of thermal plants running. However, in 5 years' time, here is what we are going to see after 2025. And the tallest nuclear power station will also be decommissioned after 2035. So we are facing a huge decrease in the number of thermal plants in a relatively short period of time. As a result of the changing generation pattern, the system is facing a large decrease in system inertia. Here's a study conducted by National Grid to show the chain of inertia change in coming years. The four different curves means 4 different possible energy development scenarios in the GB transmission system. If we take the green one as an example, currently we have about 200 GVAS inertia level. But if you have a look at the inertia level in 5 years' time, we could see up to 40% decrease of the inertia level to 120 GVAS. So this means that with the same amount of power imbalance, the system will see a larger lock-off, and that means faster frequency deviation when something happens in the system. In order to cope with such lower inertia, the system operator will also need to prepare more reserving unit in order to react to the frequency disturbance. So that will significantly increase the operational cost. Here is a simulation we conducted using an analytical model to show the impact of decreasing inertia on frequency behavior. Case 1 is close to a synchronous machine dominated system, and case 2 is similar to a system which we have in the GB at the moment. And case 3 is represents a case we're likely to see in 5 years' time if no action is taken. So you can see that with the decrease of inertia, we will see higher lock-off, and also this will result in a lower frequency nadir. And if we want to maintain the frequency nadir above the required limit, so what we have to do is either we need to limit the largest generating power so that we limit the power imbalance size, or we need to keep more synchronous machines online to maintain the inertia, or it can provide more primary response. In either case, it will significantly increase the operational cost. Another challenge is that the renewable generation is typically distributed non-uniformly in the system. So some part might have a lot of renewable generation, but the other parts might be still dominated by synchronous generators. So we start to see increasing regional variation in frequency and log off during disturbance, as shown here in this figure. So the consideration of the locational impact of the frequency disturbance becomes increasingly important and starting to become a concern to the system operator. Here is a historical event we recorded with PMU data across the GB transmission system. As you can see that when the event happens, the frequency and log-off value no longer be a uniform value across the system. If you look at here, this point, this is the log-off value here. That is where the event happens. So we can see a clear characteristic at the event location. So by analyzing the frequency and log-off along with the angle measurement data, we will be able to locate where the event is in the system, and therefore we will be able to dispatch fast frequency response closest to the location of the event. To address the frequency control challenges, as I mentioned in previous slides, a project called Efcc was initiated in the UK. The project was led by National Grid, ESO, with a number of industrial and academic partners as shown here in the slides. The project aims to use wide area monitoring signal from PMUs in order to enable faster frequency response with consideration of locational impact of the disturbances. And the system also aims to coordinate the response from different types of resources like energy storage, demand side, wind, etc., with the aim of optimizing the overall behavior with consideration of their location and capability. Here is a high-level design of the EFCC control scheme. The electrical transmission system overall is divided into a number of regions based on generator coherence grouped analysis. Within each region, there are a number of PMUs installed to collect real-time monitoring signal, and these signals are sent to a unit called regional aggregator. Each region will have one regional aggregator, and it will combine and process these measurements and produce a regional equivalent measurement to represent that region. And this signal will then send to a unit called local controller. The local controller is installed at the resource site. So each resource will have one local controller distributed across the system. So if you have an energy storage unit, you will have a local controller. And these local controllers will receive measurements from all regional aggregators. That means it has no visibility across the whole system. There is also an element called central supervisor. Now, this element mainly conducting non-real-time, near real-time communication with the local controllers to update the information about the resource availability across the system. So the local controller will update its own resource availability information to central supervisor, and the central supervisor will combine all the information and broadcast it to all local controllers. So that means local controller will understand the real-time situation of the system while PMU data, but also understand what is available locally in its resource and also understand what is available in other locations. Combining these two sets of information, you will be able to detect the event and understand how much it should contribute to respond to that event. So the whole process, we are aiming a response control signal to be sent within 500 milliseconds and deliver a response within 1 second. Because of the time, limited time, I'm not going to the detailed algorithm behind each blocks here. So for those who are interested, please refer to our paper as listed on the bottom of the slide. Now I would like to hand over to my colleague Ibrahim, who will talk you through a high-level testbed we established for testing the Efcc scheme.
Thank you, Qiteng. I would like to take you through the test setup of this project at the Power Networks Demonstration Center. So very briefly, the Power Networks Demonstration Center is a medium and low voltage distribution test network that serves as a platform for the accelerated testing of new smart grid technologies. And what I'd like to emphasize here for the purposes of this project presentation is the power supply that's used, which is a 5 MVA motor generator set. And that's used as an interface between the real-time simulator and the medium voltage 11 kV network and low voltage 400 volt network in order to implement the power hardware in the loop test implementation. And of course a 6-rack RTDS system where the network model is deployed. So this shows a high-level implementation of the power hardware in the loop setup. The test network, as I mentioned, used 11 kV and low voltage assets. The motor generator set, as you can see here on the left, and at the right, load banks have been used as controllable resources, which are deployed as a frequency response in the form of load shedding or load curtailment. The RTDS system was used to model a reduced GB transmission system with 3 distinct regions for the purposes of the frequency response. Hardware in the loop synchronization has been achieved between the 11 kV network and the RTDS via the motor generator set, and Qiteng will later on talk you through the control implementation in order to achieve that. 3 physical regional aggregators were part of the test, as well as 2 physical local controllers. An emulated central supervisor was used in order to dispatch the available resources for the frequency response. The regional aggregators were monitoring synchrophasors that are produced from virtual PMUs in the RTDS simulation. And then the aggregated information is transmitted via communication network to the local controllers for processing and determining the appropriate frequency response to any simulated disturbance. Once an event is detected and a frequency response is required, then local controller 1, for example, would control an emulated resource in the simulation via Goose messaging. And local controller 2 is able to action a control command to the load banks via Modbus. Physical PMU has also been used to feed synchrophasor information to local controller 2. And as I said, the emulated central supervisor is used to determine the availability of controllable resources and the appropriate level of dispatch on a regular basis. I'll hand over to Qiteng to talk you through the details of the power hardware in the loop synchronization and the controls required to achieve that.
Thanks, Ibrahim. Regarding the power hardware in the loop testbed, firstly, we constructed a reduced GB transmission network model in RTDS, as shown here. And we validate the model against a number of historical events. So here is one in 2012. The dashed line is from the average frequency measurement in the model, and the solid line are the actual measurements in the system. And here is another event recorded in 2016. So we created a model that is fairly representative against the real system behavior. We then interface the model with the physical network through controlling the MG set so that the physical network is synchronized with the model. Then we take the color measurement from the MG set terminal and feed it back to the model to close the loop. But using this setup, basically we couple the physical network and the model together. So in the physical network, we feel it is actually connected to the real system. And for the model, it emulates the interruption that it is connected to our actual distribution system. And because we have limited low band capacity in the system, it's about 500 TVA. So when we feed back the current signal, we can also apply the scaling factor so that it can be scaled up to a desirable size we want. So here is a high level results of the synchronization between the physical network and the model. Above is the frequency and the bottom is phase. Here is our power measurement from the low band, which here is about 50 kilowatt, and when we scale it up, to about 200 megawatt. As Ibrahim mentioned, the MG set we use is a 1 MVA generator driven by a 5 MVA motor. Compared with inverters, using MG set for power hardware in the loop is more challenging in a way that it has a much slower response due to the rotating inertia. The MG set we use is equipped with its own proprietary frequency controller as shown in this block diagram. This frequency controller has relatively poor frequency checking performance. It's not ideal for power hardware in the loop, and it does not provide any phase tracking at all as required by the synchronization. And we cannot really easily make any changes to this controller because it's shipped from the manufacturer, is built in the system. The way we tackle the problem is we treated the whole system as a black box. And then on top of that, we introduce an augmented frequency loop and an augmented phase loop in order to enable the frequency and phase tracking capability. These controllers are implemented in RTDS, so for the MG set, all it receives is still a frequency signal without making any changes to the original controller. When we perform the analysis of the whole system, it ends up with a high order dynamics. So we use internal model control for designing and tuning the controllers. The details can be found in the paper on the bottom of the slide. Here are some results from frequency checking. First plot shows that there's original frequency checking performance of the controller, original MG set controller. And the second one is with augmented frequency loop. You can see that very accurately checking the frequency during disturbance. And here is the plot showing the phase tracking. The first plot is from original controller. There's no phase tracking as mentioned before. And the second one is with the augmented phase loop. You can see that during the disturbance, you can check the maximum phase with an error about 10 degrees in this case, and they very fast reduce the error to a much smaller value. We use the testbed for testing the Efcc fast frequency control scheme discussed before. Here are two scenarios. One is with a relatively high inertia of 220 GVAS, and the other one is have a relatively low, which is 82 GVAS inertia level. So if we have a 1 gigawatt loss of generation in the system, for 220 GVAS, we typically see a frequency nadir around 49.7. But if the value decreases to 82 GVAS, we will see a frequency nadir below 49.4 if no action is taken. Obviously, we will see a much higher log curve. Now, let's have a look at how Efcc can actually improve the frequency regulation during the low inertia scenario. In this case study, we are going to look at a loss of 1 gigawatt event. And there will be two resources being controlled by the Efcc scheme. One is by local controller 1, which is a battery located in the north of the system in region 1. And we have another resource, is a demand-side resource located in region 3, which is in the south of the system. And we're going to test how the Efcc will respond to an event happened in region 1. Here are the results from the test. When an event occurs, both local controllers very quickly detect the event successfully within 1 or 2 cycles. And because the event is located in region 1, which is the location where local controller 1 is located, so Erlangen-Nürnberg deploy all of its response immediately when the event is detected with all of the reserve. And local controller 2 is located further away in region 3, so it has a delayed response with a reduced amount. And this is to avoid stressing the system in the initial period of the disturbance. And this is based on the calculation running internally in the algorithm, along with the ranking process conducted in the system. You can also see that both resources has reacted to the commands correctly. Battery has relatively faster response to the command, while the low bank has its own characteristic in responding to the command signal. But both of them are acting as required in this event. So let's have a look at the measurements from the 3 regional aggregators at the 3 different locations of the system. The green one is where the event happens in region 1. The blue one is further away in the system. You can see the frequency variation. When the event happens, the region where the event happens will have a faster frequency deviation at the initial period, and that will increase the initial angle separation of the system. And what the control action is trying to do here is try to push the frequency together so that to reduce the stress of the angle separation. As a result, if we compare the 2 cases with and without the Efcc scheme, when we introduce the frequency scheme here, Efcc control, we managed to bring the frequency nadir to a much higher value, which is above the 49.5 limit, statutory limit in the UK. So what we are trying to do here is, by replacing the conventional primary response with faster response, it is able to maintain the frequency nadir in a much more desirable level. Now let's have a look at what happens if we increase the resources size in both sides with the same event. So we have 3 cases here. Both of them have 300 megawatt, 600 megawatt, and then 1 gigawatt. You can see here, the first plot is from the same as previous case. Basically, Erlangen-Nürnberg deployed 300 megawatt. But now, if we increase this number to 1 gigawatt, we can see that Erlangen-Nürnberg has the sufficient power to cover a whole event. And that means we no longer need anything from local controller 2, because Erlangen-Nürnberg has a higher prioritized ranking in the table because it is closest to the event location. If we look at the frequency behavior, you can see here that by detecting the event much quicker and with a much faster response, we will be able to control the frequency in a more effective way. If you see, in this case, without any Efcc, the frequency can drop to 49.3. And if we have a lot of faster response, we will be able to control that within a very small deviation range. And that demonstrates the value of a faster frequency response in the future system to support the frequency regulation. Just to draw some conclusions from the presentation, so the future network is facing significant challenges associated with frequency control. And distributed energy resources shows great potential in supporting a faster frequency regulation. And we developed the Efcc scheme that aims to use wide area monitoring signals to enable fast and coordinated response from different resources, including distributed energy resources. And the power hardware in the loop testbed we established provide an ideal testing environment for validating such novel frequency control solutions like EFCC. And it also helps to de-risk any potential issues before the actual implementation. So that's all of my presentation. Thanks very much for your attention. I'm happy to take any questions. Thank you.
All right. Thank you so much, Qiteng and Ibrahim, and to Simon as well, our first presenter. And thank you to all of you for your attention and your engagement. We have had a lot of really great questions come in and some good responses to our polls, our survey questions, so we really appreciate that. I think we will start with a discussion of some of the questions. We had quite a few questions relating to the nature of power hardware in the loop work. Let's start by discussing some of the advantages and challenges of using the Aurora protocol communication for power hardware in the loop. And just to clarify, this is the practice of using that Aurora protocol rather than a conventional analog and digital hardwired interface. So Simon, did you want to discuss some of those advantages and challenges?
So hello everybody. Well, one or the major advantage of the Aurora protocol is that there is no measurement noise or no noise coupled into the communication. If we have an analog signal, then well, there is noise, and with the digital Aurora communication, it is very fast because it is based on light, but the interface is not standard for most of the power amplifiers, so it has to be specified, and well, there you need the special Aurora interface.
Absolutely. Yeah, thank you. Ibrahim and Qiteng, I'm not sure if one of you wants to comment a little bit as well on your experience.
Hello everyone. So in terms of our experience, I think using Aurora was quite helpful practically, because we had the simulator in different locations physically, so it was about a 30-meter or more separation. So running a fiber was far more practical than using analogs, which would result in a lot of interference and potential problems down the line. The thing that I would pay attention to is the implementation of the protocol on the amplifier. So you might run into some challenges if the implementation on the amplifier is not initialized properly, as well as having to look at the data point mapping between the model and RTDS and how it's defined on the amplifier side. But I think the fact that there's a limited number of amplifiers or the ones that are most commonly used, I think there's a close relationship between suppliers and RTDS in order to iron out any.
Yeah, that's a very good point. So we have worked together with some of the amplifier manufacturers to establish this interface, and there's work done on both sides. So Spitzenberger and Spies, Egston, and Triphase are all manufacturers we have worked with to iron out that interface, but it's still something certainly to be aware of. Thank you both for your comments on that.
You're welcome.
Question for Simon here on the filter. We had a couple of people asking why you chose to build the filter in Matlab, and is it possible to build in RSCAD, and what would the challenges be?
Okay, well, I think it is certainly possible to build the filter in RSCAD as well, but we chose Matlab because we could take advantage of all the filter design tools that are available in Matlab. For example, FDA tool, where you can see the body plot and the filter reaction and step response and everything like that. And then it is actually very easy to export this filter from Matlab to a C code file and import the C code via the C builder into RSCAD, and then you have it in the model library, just like all the other components, and you can use it as a block. And so the import is very easy, and well, that was the main reason why we chose Matlab for the filter design, because of all the design tools that are available in Matlab.
Excellent, thank you. We also had a couple of people asking about the bandwidth, and did you have any, obviously there's a balance between using that filter and perhaps experiencing limitations in the bandwidth. So if you could comment a little bit on that, and whether there is a minimum required bandwidth for performing the grid code compliance tests that you were working on.
Oh yes, honestly, we're still working on that point, because the filter I designed for the presentation had a cutoff frequency just starting at 50 Hertz to filter out all the harmonics and all the noise to get the highest stability as possible. I don't think that it is necessary. I think you could also switch the cutoff frequency to higher frequencies, and then you have also some harmonics. But in the investigations we made, it made no difference, because we only in this experiment there was no interest in harmonics, and that was the reason why we chose such a radical filter. But I think it's also possible with other cutoff frequencies.
Excellent. Yeah, thank you. I want to just switch channels a little bit away from the PHAL stuff and ask a question to Ibrahim and Qiteng. You were using synchrophaser data and goose commands, obviously, in your implementation. Have you done any work in emulating communication problems, either due to cyber attacks or just network conditions, maybe varying the latency or the jitter at all?
Yes, I probably require a bit more feedback from Qiteng, but however, we did use a communications emulator to emulate the wide area network, so the WAN. So that's the traffic between the regional aggregators to the controllers. The fact that the physical implementation meant the connections were all local, but in order to emulate that sort of wide area delay, so it's more realistic, as well as trying to understand what the impact of latency, jitter, or data corruption on the transmitted packet has on the controller's performance. So I believe there's public information on that as well, Qiteng.
Yeah. Sorry, I was actually speaking and realized I was muting myself. So yes, as Ibrahim mentioned, one of the key elements of the work is try to quantify the limit of the communication performance on the impact of the wide area monitoring and control system. So basically, we try to test the limit of how much data loss we can tolerate, and how long is the latency and jitter the system can tolerate, and then we try to use that to quantify the specification for supporting a wide area system, for enabling the control. We use a commercially available communication emulator to achieve that. But internally, I think we have PhD students working on developing some low cost communication emulator as well, to looking at introducing such a communication variation. But I think that work is also in collaboration with RTDS. It's still ongoing at the moment. Thanks.
Great. Thank you so much. Related to that, that quantification of latency and the determination of tolerance for latency, back in the PHIL zone, I'm wondering, we have a few questions on whether either of your teams have done work in quantifying the latency of your PHIL interface, and whether there's sort of a maximum delay for stability in your setup. And I wonder if you would comment on that, perhaps Simon first, and then Qiteng and Ibrahim if they wanted to add anything.
Mm-hmm. So we did measurements on the latency. It was about 500 microseconds, the closed loop communication delay, and that is pretty fast. So we did not discover any stability issues with that delay, but stability is nevertheless one of the crucial points in power hardware in the loop implementation. We started with ideal transformer method, which is the most simple transformer method, but we have a lot of work to do on that, because it's not that straightforward. We experience.
Right, absolutely. Qiteng and Ibrahim, I don't know if you want to comment here.
Yeah, for us, we obviously use quite a different device for enabling power hardware in the loop. So if you see the existing work, I think vast majority of them use converter-based interface to enable power hardware in the loop. But in our case, we use a motor generator set. So it is a synchronized machine. In theory, it had much slower response compared to a converter. And that is, it's not because we choose to use that, because that is a MG set available for us. And then we try to develop controller to enable hardware in the loop, a power hardware in the loop capability. So in our case, what we have to do is, we have the inertia constant of the machine is around 1.7. So if you do a step change, it's quite a significant delay. So what we have to do is, there is a limit that the system can achieve is not as dynamic as our converter-based power hardware in the loop. But for some specific application like frequency response test, that is, we found that to be sufficient. So that's why we adopted that. So what we have done is we have to lay out all the transfer functions of that MG set. It ended up a very high order dynamic system, and then we have to do some careful tuning in the controller, games, and also the parameters in order to make sure the whole system is stable. And I don't think, as Simon mentioned, I don't think there is a definite limit. It also depends on what we connected in the physical system side. So that it would depend on the closed loop control system analysis. I think that is the approach we have to adopt, and then depending on what we connected and what we have in our simulation, that might have slightly different answer, I would say. So
Great, thank you. Yes, the "it depends" answer, which is very popular in the power systems sphere. Well, I think we should probably wrap up because we're hitting our time limit here. But I want to thank all of our presenters so much for really great presentations and discussion today. And thank you for our audience for being here. We look forward to seeing you next week. And don't forget that if you access this content on demand later, you can still submit questions and they will be answered by email. And please feel free to reach out to our team or to any of the presenters if you wish to have a discussion offline as well. So thank you to all of our presenters, and I hope everyone has a great day.
Thanks very much.
Thank you as well.
Thank you. Bye-bye.